So let's take all of this information and put it together. We've talked about limits in chapter 1. We've talked about finding the area under the curve, and that's what integration does. We've talked about left and right sums in these rectangles, overestimating or underestimating the curve depending on if they are circumscribed or inscribed. And we talked about sigma notation and summations. So what if we want the widths of the rectangles? Maybe we don't want 4 rectangles, or maybe we don't want 8 rectangles. Maybe we want n rectangles. So we're talking about, a whole bunch of rectangles. And what is that area going to be? So to find how wide the rectangles are, it still might b minus a divided by n. Only now, instead of n being a number, we're going to leave it generic. So in this case, these rectangles are going to be 3 over n units wide. So let's use that summation notation. We're going to add a whole bunch of rectangles together. So we're going to go from 1 to n rectangles. In the last example, in the last video, we only added 4 rectangles together. But now we want to add just a whole bunch of them. So graph-wise, here's our graph. This is a rough sketch of 3x minus 2. We want to know what's happening between 2 and then 5. So we could split this up into 3 rectangles and get an okay estimate, or we could go 6 rectangles and get a better estimate, or we can go n rectangles and get an even better estimate about what's going on. And our goal is going to be to come up with some kind of formula to describe this, and then take the limit as n goes to infinity. So let's go. We know when we find the area of each rectangle, it's always length times width. So in this case, each rectangle is going to be 3 over n units wide. We just got to figure out how wide it's going to be. How tall is it going to be? And remember, in the last video, we talked about how tall is really based on that equation. So if we were to have delta x, let's say that's 1 unit, because we're looking at just 3 rectangles. And we wanted that upper sum. Then to get to this guy, it would be 2 plus 1 to get that rectangle. And then it would be, which would put us at 3. And then to get the rectangle here, it would be 2 plus 2 to get to this value of 4. And then to get to that value of 5, it would be 2 plus 3. So you can see how if we could start here and get to whatever this x value is by adding increments of delta x, if delta x were 1. We're going to do the same kind of concept here. We need to evaluate the function at some x value. We're going to start at this 2, and we're going to increment by 3 over n, and we're going to multiply that by I. So this will go in for that x value. This is going to tell us how tall that rectangle is. So it's going to be 3 times 2 plus 3i over n minus 2. So let's do some distributing here. So this is going to be 6 plus 9i over n minus 2. Six minus 2 is 4. If we were to distribute that, we're going to have 12 over n plus 27i over n squared. So we could write this way. Now, think about what this means. I'm replacing I with 1, then with 2, then with 3, all the way up to n. Okay, this guy doesn't have an I in it, so we're actually treating this like a constant. So we could actually view that as 12 over n times n. Okay, using that constant formula. And then if we look at this guy, that 27 over n squared is not affected by this. That's just a constant value that's being multiplied by each number. So we could rewrite that this way. So then if we were to pull this up here, those n's reduce. So I'm doing some reducing as I work through this. And then we have 27 over n squared. And then this guy, if you remember, had a formula. That was Gauss's formula that we talked about. So that's the same thing as n times n plus 1 over 2. So we have 12 plus, I'm going to reorder this, 27 over 2, and that's n squared plus n over n squared. So if we reduce, this is n squared over n squared plus 1 over n squared, which is going to reduce to 1 plus 1 over n squared. So we have 12 plus 27 over 2 plus 27 over 2n squared. So there's our sum. That's what they're calling S sub n here. This guy is a right sum. It's going to overestimate. So now, let's look at what's going on here. We have this written in terms of n. Let's take the limit as n goes to infinity. So what this is saying is as we add more and more rectangles, where is that limit going to go? If we take 12 and we add 27 to it, we're going to get 39. Sorry, 12 plus 27 over 2 is 51 over 2. Plus 27 over 2n squared. So as we take that limit, 51 over 2 goes to 51 over 2. But as n gets bigger and bigger, this second term is going to head to 0. So this whole thing is just going to 51 over 2. So it turns out that the area under this particular curve would be 51 over 2. So that's finding the area using the limit process. Just for fun, let's do another one. Let's say we're looking at y equals x squared plus 2 on the interval from 0 to 1. So the process is going to work the same way. We know what this guy looks like. X squared plus 2 is going to look like this. X squared shifted up 2 units. We want to know the area between 0 and 1. So what is this area in here? And we can use that limit process to help us do that. So once again, we have to figure out how wide are those rectangles. It's always b minus a divided by n. In this case, it's going to be 1 minus 0 divided by n, which is 1 over n. So to find our sum formula, we're adding the area of a whole bunch of rectangles together. So we need to know the length and we need to know the width. In this case, we already know how long they are. We said they're 1 over n units. But to find the width, we're going to have to use that sigma notation. So where are we starting? In this case, we're starting at 0. And we are incrementing by 1 over n units times I. So this is going to simplify to I over n. So let's talk about what that means again. Let's say we were talking about 2 rectangles. So let's pretend we're talking about 2 rectangles. Okay, so we're starting at 0. We want to go to 1. If we're talking about 2 rectangles, then they have a width of 1/2. So the way you get the expression in here, you have to figure out where you're starting and how do you get to the next increment. So we're starting at 0, so that's where the 0 comes from. We are adding, in this case it would be 1/2 unit to get to this number. So we would evaluate that height. Here's a rectangle at 1/2. So it would be 0 plus 1/2 would get us to 1/2. To get to this one, our second rectangle, it would be the starting point plus the increment times what rectangle we're working on, which would be the second rectangle. And that would put us at that value of 1. So if we're doing that for n rectangles, it's starting point plus the increment times what rectangle we're working on, whether it's the first, the second, the third, the 53rd, so on. So that's why we're using an I there. This has to go inside of the function. That's going to tell us how tall the rectangle is. So our function is x squared plus 2. And now we just want to do some algebra and simplify that as much as we can. So we have 1 over n here. This is I squared over n squared plus 2. And then I'm going to distribute this to everything in here. So we have I squared over n cubed plus 2 over n. So then I'm going to split the sum apart. I think it makes it easier to think about it. So keep in mind, this is really an understood 1 in the top over n cubed. That is just a constant, so it can come out. So we can rewrite it that way. This guy is a constant. So we have that constant times n. So we're reducing that. Now, this guy has a formula that's associated with it. Thinking back to that earlier theorem, the sum of I squared was n times n plus 1 times 2n plus 1 all over 6. And then I'm going to reduce this to 2. So I'm kind of doing a few steps in one here. We reduced that summation using that summation for a constant. That's where that came from. And then we substituted that red one in for this, or substituted this in for that red one that I circled. So now we need to simplify this. That n and this will reduce. So we're going to have 6n squared in the denominator. Now we need to FOIL all this out. So we have 2n squared plus n plus 2n is plus 3n plus 1. And then we have a plus 2 hanging out. We can split that numerator. So this is going to reduce to 1 over 3. This reduces to 1 over 2n. This stays the same. And then we have a plus 2. So we have 2 plus a third, which is 7/3, plus 1 over 2n, plus 1 over 6n squared. So there's our sum formula. So now, let's take the limit as n goes to infinity. So, as n goes to infinity, 7/3 is going to go to 7/3. But 1 over 2n, as n gets bigger and bigger, that n is in the denominator, so that whole fraction is going to get smaller and smaller, and it's going to approach 0. The same thing is going to be true for that second one. That guy's going to go to 0. So, our area is going to be 7/3. So that's the area using that limit process.